Welcome to this explainer. Step into the Colosseum of Cambridge exams. Seriously, taking these papers can feel like an absolute battle, and let's be real, only the prepared survive. Today, we are going to do something highly practical, highly tactical, and honestly, a real game changer for your revision. We are taking a dense, intimidating list of Cambridge IGCSE multiple choice questions, specifically from the additional Mathematics 0606 syllabus, and we are transforming them into a clear, structured, mathematical masterclass. If you've ever opened a past paper and felt just completely overwhelmed by the sheer variety of problems jumping out at you, trying to figure out where to even begin, well, you are in the exact right place. Because in this arena, there are usually two types of students who struggle. There are the ones who overload themselves with raw mathematical facts, but zero analysis. And then there are the ones who just rush. They rush right through, totally missing the command word requirements in the question. We are going to make sure you are neither of those. We are going to decode the logic behind the exam step by step so you can walk in there like a true strategist. Okay, let's look at our battle plan. We are grouping our attack into three distinct arenas. First up, numerical foundations. Then, algebraic mastery. And finally, spatial and geometric reasoning. This thematic structure is the absolute secret to actually retaining what you learn instead of just memorizing isolated tricks. All right, Section 1, Numerical Foundations. We are kicking things off by mastering arithmetic and surds. This is where we manipulate irrational numbers and exponents to build up your baseline confidence. Let's dive right into Question 5 from our review document. Work out the exact value of 2 root 6 times 5 root 10. Write your answer as simply as possible. Now listen closely, because this directly tests your ability to correctly multiply and simplify irrational numbers. But more importantly, look at those command words, exact value and as simply as possible. What does that actually mean for you in the exam hall? It means no decimals from your calculator, period. And it means absolutely no leaving large, chunky numbers trapped under that square root sign. If you just punch this into a calculator and write down a long string of decimals, you are going to lose the marks, even if the decimal equivalent is technically correct. They want to see the exact surd form fully broken down. But before we even pick up a pen to solve it, I want you to lock in your answer mentally by looking at the multiple choice options the exam board provides. This is a crucial strategy. We have option A, 20 root 15, option B, root 600, option C, 7 root 60, and option D, 10 root 16. Just scanning these, you can instantly see what the examiner is trying to do. They are testing whether you know exactly how far to take that simplification process. Which one of these is truly the simplest form? Root 600 looks massive. Root 16 is literally just a perfect square hiding in disguise, right? Because the square root of 16 is 4. So the exam board is laying out traps. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's actually solve this thing and navigate around those traps. Let's break it down into a foolproof blueprint. Notice how we treat the coefficients, the outside numbers, and the square roots as completely separate entities before recombining them at the very end. This is how you avoid careless errors. Step 1, we multiply the outside whole numbers. 2 times 5 gives us 10. Easy enough. Step 2, we multiply the inside surds. Root 6 times root 10 gives us root 60. So now we have 10 root 60. But wait, are we done? No way. Remember that command phrase, as simply as possible? We have to simplify root 60. How do we do that? By pulling out the highest perfect square that divides evenly into 60. In this case, that's 4, because 4 times 15 is 60. The square root of 4 is a neat whole 2. That leaves the 15 stuck inside the root. So root 60 becomes 2 root 15. Finally, step 4, multiply that newly extracted 2 by our original outside 10. 10 times 2 is 20, giving us our final, fully simplified answer, 20 root 15. So the absolutely crucial point here is that if you had stopped at root 600 or 10 root 60, you would lose the points. They are technically the same mathematical value, sure, but those answers completely ignore the command to write it as simply as possible. Following our methodical simplification leads us perfectly and safely to option A. Okay, let's elevate the complexity. Section 2, Algebraic Mastery. This is the arena where you prove you can manipulate variables and handle letters with the exact same confidence as numbers. Looking at question 12, this brilliantly illustrates the fundamental difference between an expanded polynomial on the left and its fully factorized form on the right.
The question on your paper would ask you to fully factorize 15x squared y plus 25xy squared. Now, to get the neat expression on the right, we've carefully scanned the terms and extracted the highest common factors. This is like looking for the common DNA between the two parts. First, look at the numbers, 15 and 25. What's the biggest number that divides into both? It's 5. Now look at the letters. We have an x squared and an x. They both share at least one x. We have a y and a y squared. They both share at least one y. So pulling that 5xy to the outside of the bracket is our first major move. Then you just figure out what's left behind. 15 divided by 5 is 3. X squared divided by x is x. The y is pulled out completely, so the first inside term is 3x. Do the same for the second term and you're left with 5y, giving us 5xy times the quantity 3x plus 5y.
Let's tackle another algebraic challenge with question 8. Now, I have to warn you, this one is a fantastic trap for students who rush and forget their basic index laws. The prompt is incredibly short. It just says, simplify x times the quantity 4x to the power of 6 squared. It looks so small, right? But do not be fooled. There are multiple operations competing for your attention here. You've got multiplication, you've got powers, you've got parentheses. If you try to do this all in one go, your brain is going to cross its wires. Before we reveal the breakdown, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's dismantle this trap step by step. By visualizing this in stages, you can see exactly why you must square the number 4 completely independently of multiplying that power of 6. Step 1, the square on the outside applies to everything inside that bracket, so 4 squared is 16. Step 2, a power raised to another power means we multiply the powers. So x to the 6th squared becomes x to the 12th, 6 times 2. Step 3, we bring down that lonely x hanging out at the front. Now we have x multiplied by the quantity 16x to the 12th. Step 4 is where the magic happens. Remember that a lone x is actually x to the power of 1. When you multiply terms that have the exact same base, in this case x, you add the exponents, so 1 plus 12 gives us 13. Landing on exactly 16x to the power of 13 proves a major point. Methodical algebraic steps absolutely prevent simple calculation errors under pressure. If you had tried to be a hero and do this all in your head at once, you might have accidentally added the 6 and 2 to get 8, or completely forgotten to square the 4 and just left it as 4. Structure is your best friend in this arena. Finally, we enter the third arena, spatial and geometric reasoning. This is where we take all those numerical and algebraic tools we just sharpened and apply them to the physical world, stepping off the abstract page to actually measure sides, angles, and distances. Question 18 is going to require us to ground ourselves in a true classic, Pythagoras' theorem. But pay attention, because here we're specifically focusing on how to find a missing, shorter side, rather than just plugging in numbers to find the hypotenuse. We all know a squared plus b squared equals c squared. You probably learned that years ago. But the real test in the 0606 exam is rearranging that formula properly when c, the longest side, is already known. So here's the scenario they throw at you. We are given an intimidatingly large hypotenuse of 145 centimeters. We are given another side of 143 centimeters, and we are tasked with finding the remaining side, marked x. When you see numbers in the hundreds like this, it's really easy to freeze up. The numbers might seem scary, but the underlying principle remains exactly the same as if the sides were 3, 4, and 5. Now, what's really interesting here, and this is a pro-level exam tactic, is that using basic common sense and spatial reasoning, you can immediately eliminate options A and B. Why? Because a shorter side can never, ever exceed the hypotenuse. The hypotenuse is, by definition, the longest side of a right-angled triangle. Since our hypotenuse is 145, option A at 204 and option B at 576 are mathematically impossible. They are trap answers for students who accidentally add instead of subtract in their formula. You've instantly reduced this to a 50-50 guess before writing down a single equation. That is how you play the game. Let's run the actual numbers through our rearranged Pythagorean formula. Step 1, we set it up. X squared plus 143 squared equals 145 squared. Step 2, we rearrange to isolate our unknown. So x squared equals 145 squared minus 143 squared. Step 3, we calculate the difference of those squares. 145 squared is a massive 200,025.
143 squared is 20,449. But look what happens when you subtract them. Those massive thousands dwindle down beautifully, and rather politely, to a perfect square of 576. This is a fantastic reminder not to panic when you see giant numbers on a Cambridge paper. They are almost always designed by the examiners to collapse into something clean and manageable if you use the right method.
So for step 4, taking the square root of 576 gives us precisely 24. 24 centimeters, this perfectly verifies that option D is our correct geometric answer. No guessing required.
Let's close out our thematic review with question 20, which deals with bearings. Now, you must keep in mind the strict navigational rule for these. Bearings are always measured clockwise from the north direction, and they are typically written as 3 digits. Bearings often trip students up because they require a real shift in perspective. You have to imagine yourself standing at a specific point on the map and turning your body. Here is the question. The bearing of Zurich from London is 126 degrees. Find the bearing of London from Zurich. This is a classic perspective shift problem. If we know the outbound clockwise angle from London to Zurich is 126 degrees, how do we calculate the return journey? We have to figure out the bearing of London from Zurich. That word "from" is your anchor point. You absolutely cannot just do this in your head. You need to sketch it. Step 1, draw parallel vertical north lines at both cities on your page. By doing this, we can use our parallel angle rules. Imagine the straight line connecting London to Zurich acting as a transversal, cutting across those 2 parallel north lines. This allows us to find the co-interior angle inside those parallel lines. Co-interior angles add up to 180 degrees. So 180 degrees minus our 126-degree outbound bearing leaves us with an interior angle of 54 degrees at Zurich. But remember the golden rule. Bearings must be measured clockwise from north. That 54 degrees is counterclockwise. So for step 3, we simply subtract that 54-degree interior angle from a full 360-degree circle to find the massive outside angle. Now, before we reveal that final number, listen closely. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. And when we subtract 54 from 360, it reveals the return bearing is exactly 306 degrees. This perfectly showcases how abstract geometric properties, like parallel transversals, interlock directly with real-world navigational rules to give us option D. So, let's recap our masterclass blueprint. By organizing your studying into these thematic arenas, numerical, algebraic, and spatial, and utilizing step-by-step deconstructions, you can dismantle absolutely any intimidating mathematics paper. Don't just stare at a massive list of 20 questions and let cognitive overload freeze you. Group them. Break the multiple choice options down before you calculate. Use spatial logic to rule out the absurd options immediately, like we did with Pythagoras. And always lean on your core foundational rules. Simplify your certs fully, watch those tricky exponent laws, and always measure your bearings clockwise from north. I'll leave you with this final, crucial question. Be honest with yourself. Based on the concepts we explored in the Colosseum today, which specific mathematical arena, numerical, algebraic, or geometric, do you need to train in the most to master your upcoming exam? Identify your weakest link right now. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.